Okay. This one, Form 6 GCE. Okay, so these videos will try to explain about capacitance. So according to your syllabus, capacitance is 19 capacitance. And then we are in 19.1. Essentially, it's just talk about capacitors and capacitance. Lowercase. So what is capacitors and capacitance? I think first of all, before we learned this topic of capacitance, we were in the topic of electric field. In there, we study one type of configuration, that is, you are given two parallel metal plates, and then what you do is that you put some charges on one plate, and then you put some other charges on the other plate. I use negative here. And then we claim that there will be electric field going from the positive plate to the negative plate. Okay. So previously, we focused on the electric field strength between these parallel plates. And then here, the formula for the electric field strength is E equals to delta V over delta D, where the delta D is the plate separation, and V is the potential difference you applied across it. Well, however, then this so-called a configuration of having two parallel metal plates is already actually a capacitor. So what is really this capacitor? Will be just two parallel metal plates. However, the focus we have here is not to study the electric field strength of the electric field between these two parallel metal plates. Instead, now we focus on the ability that these capacitor can store charges. So we don't care about the electric field anymore, but we just look at this as a device that can store charges. Well, when we look at it in this way, then we can talk about two parameters first. The first of all, of course, is about the charge on this capacitor. Since the positive charge and the negative charge, they are of equal magnitude on a capacitor, then therefore, we just need to use 1Q to denote it. So here will be the charge stored on a capacitor, on it, stored, is called Q here in the unit of coulombs. But on the other hand, in order for you to prepare such a amount of charge on the two plates, then you need to connect this to a potential difference. Then the corresponding potential difference will be another parameter in the questions, which is the potential difference V in volts. Then we define something called capacitance, which is telling us about how good this capacitor is in storing charges as the capacitance. So the symbols for capacitance is C, and then C equals to Q over V. So this will be the definition of capacitance. So we suppose you to record this equation, your examination, and this C here will be the capacitance. And this is in the unit of farad, F. So we can say that we can define the capacitance in the equation is Q over C, but in words, it means the following. The capacitance of a capacitor is the amount of charge it can store per unit potential difference applied across it. Well, for example, to build some intuitive understanding, let's look at an example. Also, let us also introduce the notation as well. The notation, we look at the notation first. We will need to draw circuit diagram and then the circuit symbols of a capacitor. Will be a pair of parallel lines, but of equal length. This basically we sample the fact that we take capacitor as just two parallel metal plates. This is kind of similar to the symbol of the cell, but don't confuse them because for the capacitor, we found that the two lines here, they are of equal length. For a cell, they are of unequal length. This is something we need to pay attention to that. So therefore, for example, let's say I have a capacitor that is connected to a battery. So at first, let's say there will be no charge on the capacitor. But what does the cell do? The cell basically is to provide the EMF to drive current. Here, we take the current as the conventional current so that you have some positive charges flow in this way. But where are those positive charges come from? Well, these positive charges should come from the plate on the right-hand side. And this positive charge will go to the plane on the left-hand side. So therefore, over time, what will happen is that the plane on the right-hand side will have less positive charge. Therefore, it will become negatively charged. While the plate on the left-hand side will accumulate more and more positive charge, so it becomes positively charged. So in this case, first of all, you can see why when you have certain negative charges on the right-hand side of the plane, then you will have the same magnitude but opposite charge on the other plane. So therefore, you just need to use one value of Q to denote that. So let's say suppose now we are able to accumulate 4 coulombs of charge. Let's say on one side is 4 microcoulombs, on the other side is 4 microcoulomb as well, positive 4. So therefore, Q is equals to 4 times 10 to the power minus 6. Now we use the absolute value here. And let's say suppose the cell we have used is a, let's say, 3 volts. Let's say just 2 volts. I don't want to pick a calculator. 2 volts. Then, therefore, that means the potential difference is 2 volts. Then I can just calculate the capacitance C to be equals to Q over V. So that means it's equals to 4 times 10 to the power minus 6 divided by 2. So it's 2 times 10 to the power minus 6 farad. That means it's equals to 2 microfarad. So from this example, what do you see is that this is how we calculate the capacitance of a device, of course, but we can also think about it. What if I have a more charge? Let's say I do not have just 4 microcoulombs. Let's say I have 14 or 40 microcoulombs in it. Then that means it will affect the value of Q. Hence, I will affect the value of C, and then C will become larger. Agree? So therefore, if you can have more charges stored on a capacitor, then it means that with the same cell here, then you can put more charges on it. That means this capacitor has a more ability to store charges. So in other words, it means that capacitance, what is the meaning of it? Although the formal definition is Q over V, but you can understood as the measure of the ability for a capacitor to store charges. Ability, not capacity. It's not to say how many charges it can store before it explodes, but it's the ability. Larger the capacitance, it means that this capacitor can store more charges in this case. So now this is what we talk about a capacitor here. You may also have the idea that this capacitor, after you store the charges, what can it be used? Well, it turns out that it can be used as like a cell. For example, if you are talking about your cell phone, you have a battery in it, where you need to charge it, then that means that is actually storing some energy. We'll talk about more on this, about the energy that you can store on this capacitor in 19.2. We'll talk about this later. However, this example also want to draw the attention to you that there are actually no positive charges that jumping from the one plane of the capacitor to another plane. Because you see, all you have is just the positive charge start from one plane here and then go around and then go to the other plane. And then they get stuck there. They are not able to jump from one plane to another plane. So therefore, although it seems like you take it as a whole, it seems like you have charges going out like this, charges going in like this, but the charge that go in, let's say I call it this Tom, is not the same as the positive charge that going out, having another name called Mary. Although it seems like there's a charge to flow in, therefore we can still talk about, or you can have a charges to flow through it as if is it the case, so that you can still talk about currents. But actually, if you have the ability to like color each charge, then you find out that they are actually not the same. We will need to bear this in mind. Okay, we finish here and then we continue on the next video.